This is a follow-up to Chapter 4. It will cover loop unrolling, as I said I would mention in Part 2. This also is going to cover some additional topics like exception handling and no-op when commands become a no-op, because your peers had some really good questions. And as I mentioned in Part 2, some of the pictures in the book can be misleading. They're like primers. They're just to set you up for further reading. But if you stop at any point and assume that's the totality of the subject, it can leave you with a misunderstanding, because they're just setting you up as a primer to help you understand more later. So let's talk about explaining some of the questions your peers had here. So your peers recently asked me a question on the no operation command again when we got into a situation here. I'm going to it right here. Okay, so in the previous video, I'm not going to spend a lot of time on this because I already talked about it, but we can't go back in time. Even if we have a feedback of some sort of mechanism, we still can't go back in time. Here's clock cycle 1, clock cycle 2, clock cycle 3, clock cycle 4. So I called this out in the previous video that, hey, this is a problem. You can't just write back to the previous clock cycle, right? So in order for this to work, there has to be some sort of stall. So the book makes it look like this. It says and becomes no-op, right? So that if you look at this previous slide right here, load word and or, right? Load word and or, right? And like I said, we can't go back in time. So to deal with this, what the words the book puts here, and it's misleading, is and becomes no-op. Well, what does that mean? Well, it depends on the situation. As I talked about in Part 2, the additional logic and control added to the CPU now for the MIPS example has some detection, right, in early stages, in the first couple stages, for if there's a dependency between commands, right? And so it ought to detect when there's a dependency and deal with it. But sometimes you get a situation, I'm going to treat this as an exception, okay? It ought to have detected this earlier, because you can see right here, load word is 2, the and, it's getting loaded into 2, and the and is an anding of 2 and 5 getting loaded into 4, so clearly there's a dependency. So it ought to have detected this, but for example, and because your peers asked a good question on this, and to go along with the drawing here, how does and become no-op? Well, let's treat it as an exception, right? So let's go to the text, and I'll show you how it treats it as an exception. So in the text, all right, here's the picture we were just looking at, right? And becomes no-op, right? So no operation command. How does that happen? Well, what happens is we've shown all this logic for detection, right? But what if we don't detect something until it gets to the point that the instructions have already been issued and everything is in the pipeline? We need to deal with that. So the way we deal with that is we add additional logic. So we add additional logic right here called flush. And essentially the flush occurs, right, and is built in depending on where the detection of an exception occurs. So if it's in the instruction fetch stage that we want to accomplish the flush, we issue it from here. If it's in the decode stage, if it's in the execute stage, okay? If it's after that, I mean, it's too late, right? You're already writing it to memory. It's not useful. Well, what does a flush do? The flush is an exception handling. So they give an example here, right? They have sub and or shift and then load word, right? And we're going to look at this. Well, why the flush? The flush is a way to deal with the exception handling, because you know in MIPS we have the EPC, which is the exception program counter, and that's useful because it stores whenever we have an exception where was that in memory that the exception occurred, right? So we can find out if it was an instruction or if it was memory, what caused the exception. So we need to store that, right? So that's what the flush does. Is the flush will allow us, as it talks about here in the book, to save the address plus 4. So exception handling the software routine must subtract 4 from the save value. Shows the version of the data path so that we save where it was, okay, that we had the exception. And that's what the flush does. Plus it issues a no-op. So essentially the flush right here turns in whatever stage for some reason is detected late into a no-op, but it also, depending on the stage, well always, but depending on the stage, will deal with the PC appropriately, ensures that the PC makes it all the way through, so we store that to the EPC. So here's the example they give in the book. It's pretty good, or it's reasonable to understand. So here was the set of instructions in this order, right, and the program counter. Okay, and then as we go through each of these instructions, right, they presuppose, okay, let's say that the exception begins like this, right, and it occurs in the add instruction. So let's look at that. So it occurs right here, okay, because of some dependency that wasn't taken care of up here, okay. So the exception happens in the add, right? So what would that look like now issuing this flush in the piped CPU? Again, one more time here. Let me show you. So add, shift left, load word, okay? So the exception happens in add, and the picture here is pretty useful. So here's what it looks like, right? So we have, these were the instructions that you saw above, right? And they're making their way through the pipeline, right? So and is already done essentially, or is almost done. Add is in the execute stage. Shift left is in the decode, and load word is in being fetched. Okay, but right now we detect late for some reason the dependency, and we have to deal with it as an exception. Okay, so we deal with the exception and we issue a flush. Well, what does that do? Well, these two words will continue and make it through, but everything prior that might be in the decode, right, because of the logic, the way it's built, is going to get flushed. So you'll see what that looks like. So this, right here, so load word, shift left, both, you can see right here, get blown away right here, okay? So because those move, right, from here to here, here to here, because they're supposed to be moving along in the pipe, right? And then the add right here gets replaced with a no-op, and the or that was right here moves down to here. So in that kind of misleading picture of right here where it says stall inserted here bubble, it's kind of a misleading explanation, but essentially you're dealing with an exception. And so you have to have additional logic here to deal with that exception, and because it's an exception, then you need a way in the logic to store that in the EPC, the exception program counter, and not to lose that value. And the way we do that is with a flush. And this is the cost. Now these three commands got blown away. Now we have to issue a new command, store word, to store what was the value of the program counter when the exception occurred. Then we can go back to what we are doing. So you can read more about this in the text if you want. That's a kind of somewhat middle level discussion on exceptions and on what really happens, but good question by your peer. And so that's kind of what's going on, and that's how exceptions are handled. This is called there's a couple terms for this. There's a couple ways computers deal with it, and I'm going to touch on this here because we're going to see it again in Chapter 5. It's called a trap of certain routines, and then control sometimes in a trap is handed over to the operating system for it to decide what to do, which means additional instructions have to be issued, because when a trap occurs, then it invokes the operating system, and the operating system comes in and takes control over the CPU, assuming there's just a single core here, and it loads everything it needs to into memory and into the registers, and to figure out what happened with this program that caused an exception. Okay, That's that. I want to move on. So let's talk about loop unrolling. So I'm not going to talk about static or dynamic multiple issue here, but I am going to just mention on loop unrolling because I said I would talk about it. So here's a good example they give in the book of loop unrolling. When we have a loop that looks like this, okay? So load word, add unsigned, store word, add immediate, and branch not equal, okay? And they do a pretty good job with the commenting here, right? So what's this loop doing, right? It's loading a word, right? An array element in this case, right? So we're dealing with an array, okay? It's adding a scalar to that, right? Whatever was loaded is going to get added and then saved over, right? So we're just using temp registers here over and over again. Okay, and then we're going to store whatever the result was back out, and we're going to put it in save memory here. And then we're going to decrement our pointer, right? So after we decrement the pointer, then we check to see if it's time to break out of the loop or to return back up to the top. Well, this is how you accomplish loop unrolling. So something they do kind of first nice, and this would be a great exam question, is they reorder it. They say, how could we reorder this to so there's no stalls to deal with dependencies. So right here we can see there's obvious dependencies in these first three commands. So this is what they recommend. I think it's a reasonable solution. Ignore right now that it's doing multiple issue. I'm not going to talk about that in this post. So they put the first command as load word. We have to have it, okay? But while that's working its way, right, into fetch and decode, then we're going to issue add immediate. We're going to decrement the counter, right? Because there's no dependency between this and this as it's working its way through the pipeline. Now, as they're working their way through, these two have worked their way through the pipeline, we may be at a place, this assumes multiple issue, but presume we're at a place where now this is to execute in the stage in the pipeline, and it's loaded, and now we can write back in time for add unsigned. So now we can finally add whatever the array value is, and then we can store it, and then we can determine if we're branching, okay? So this shows a multiple issue, but for us, for reorder, right, it would be load word, add, immediate, add unsigned, store, and then or branch not equal, either one, because you may need more time with branch not equal first to make sure this gets to execute before store word. Kind of seems out of order, but it's reordered so we don't have any stalls, okay? But that doesn't answer the question, what is loop unrolling, right? Well, here's what loop unrolling looks like. So based on the example we give, it looks like the instructions in that loop, it's going to go through it 4 times, okay? It's going to go through there 4 times. It's going to execute the loop 4 times, so it's going to mess with 4 array elements, update them, and then close. So here's where they explain that right here. Assume the loop index is a multiple of 4, okay? And so what we're going to do is, knowing that it's going to issue 4 times, instead of let me get there. Instead of doing this 4 times, knowing that that's when it's going to complete and finish its execute, why don't we just unroll it? Why don't we just issue all those commands and the branch not equal last? So that's what this looks like, right? So that means, and they spell it out pretty good right here, it means that after unrolling and eliminating unnecessary loop overhead instructions, the loop will contain 4 copies of load word, because those are all separate cases, of add and store word, and 1 add I and 1 B and E. Branch not equal, right? So let's see what that looks like. Well, this is the loop unrolled right here. This is kind of confusing because it's multiple issues, so this is kind of presuming it's going through 2 CPU pipes at the same time, simultaneously. But basically, right up front, we deal with decrementing the counter. It's kind of fictitious because we know the end of this example, the beginning and the end already, but we decrement the counter for all 4
instances that we iterate through the loop. So we just decrement it for the 4 multiplicity right here instead of doing it 4 times at 4 each. All right. Then what we do is we load word 4 times, right, for each of the different words that we need, right, or the array elements, I should say. Okay. And then we add them, right, the 4 times. Okay. And then we store them the 4 times. And then finally, we execute the branch not equal, which again, this is somewhat fictitious example because we know the beginning and end of this. The CPU has to do a lot more work to unroll this, but we unroll this. So this is an example of loop unrolling, and there's a significant savings, and this is kind of how I want to close up this mini portion here real quick of recording is what's the point of all this, right? What's the point of, and the book talks about it here, dynamic multiple issue or static multiple issue, issuing multiple instructions. I won't go into that in detail in this one, but what's the point of, why are we loop unrolling? Why are we dealing with all these stalls? Why are we dealing with write backs and all these things? Well, we're trying to drive down that CPI, right? Because if we can drive down the cycles per instruction, right, essentially we're increasing our overall performance, and the book talks about it right here, right? It's that when we, for example, when we just reorder these, right, we might get a 0.8 CPI, right, versus what it was before, I think of 2 or 1. And the argument they make is, hey, let's try to get it down even further. Also worth mentioning, the text talks about, well, we could count no ops as successfully executed instructions, but that really doesn't meet, like, that's not really ethical, right? That doesn't really meet the intent here, because as it says, doing so would improve CPI but not performance. So it'd be a false positive because we have a better CPI, so we're under 1, but not improved performance. And ideally, right, we have you know, we'd love to get it down. If we have 5 stages, right, we'd love to get as many instructions done per cycle as possible. Okay, so that's loop unrolling and reordering, retouching on why we'd reorder, and then answering the question on how does an AND become a no-op or an add become a no-op. There's actually additional logic there.